All right, so the third talk is titled Training Robots to Evaluate Robots, Example-Based Interactive Reward Functions for Policy Learning, and it's presented by Kun Wang. So Kun, over to you.
Thank you for the introduction. Hello, everyone. I'm Kun, a machine learning engineer at Cruise. I'm really excited today to present our paper, Training Robots to Evaluate Robots. This is a joint work done when I was at the University of Pennsylvania, together with Edward Hu and Professor Dinesh Jayaraman. I'd like to start the presentation with a very common reward scenario where the task is to close and lock a door. It's a very simple task, and we just need to close the door, insert the key, and turn the key knob to lock it. But if you're like me, I always want to make sure that the door is locked by trying to reopen it. What's interesting here about this is that we are using physical interaction to uncover the true state of the door. In this talk, we are trying to answer, how do we teach a robot to achieve these kind of behaviors? But first, what's the typical way of specifying a task to a robot? Here's a common picture of a perception action loop, where perception produces state estimations, which then drive action decisions. In reinforcement learning, an engineer will usually write a dense reward function to specify a task, but this requires painstaking effort, and it must be repeated for every new task. To overcome this difficulty, one promising task specification framework is exemplary rewards. A human user can easily tell the robot what the task is merely by showing it image examples of what the environment should look like after a successful execution, such as images of locked doors, or in a different task, a water bottle with tightened cap. Then the robot performs RIL with the aim of altering the environment to generate observations that's similar to those examples. So here, perception happens not only during state estimation, but also during reward estimation. But is it always possible to reliably perceive this reward? The answer is no. Perceiving task reward is actually very hard in some cases. For example, in the door locking task we just talked about, lock and unlock doors look the same. Or in the water bottle closing task, a tight and loose bottle cap are visually very similar to each other. In these partially observed settings, perceiving the task reward from passive visual observations is not possible. Instead, a human might try to open the door to check if it's locked, or turn the water bottle upside down to confirm that it does not leak. Based on this idea, we propose to train interactive reward function policies that can interactively evaluate task policy outcomes. Then the question becomes how to train this. Our solution involves replacing image snapshot examples with what we call actionable examples, real physical objects on which an agent can act. For example, it can be a physical door that the robot can open or close, or a water bottle that can be flipped upside down. Note that we get only the objects, not demonstrations, but we'll soon talk about how to learn this kind of disambiguity in action policies. So now, instead of providing image examples of the success state, we provide actionable examples of success and train an interactive reward function policy, in short, LIRF policy, to perceive the task reward. In other words, this is the policy that's going to learn to push the door or flip the water bottle to check for task completion. So how do you train the LIRF policy? We already have possible examples of successful outcomes provided by the human user, such as locked doors. In addition to this, we will add negative examples, which are simply the outcomes of the current suboptimal task policy. Then the LIRF policy is trained to interactively distinguish the positive examples from the negative examples. This is how the LIRF policy learns good verification behavior. The final outcome of running the LIRF policy is thus an automatically inferred reward. It is high only if the door is properly locked. This reward can now be used to improve the task policy. It encourages the task policy to actually lock the door, then simply push it into place. We call this final improved task policy the LIRF task policy, short for learning from interactive reward functions. As a bonus, the IRF policy the LIRF policy can even run at test time as an in-the-loop verification behavior. So basically, we will run the task policy until the LIRF evaluation looks good. To recap our key idea in all of this, we train intermediate IL policies called LIRF policies that provide rewards for training the final LIRF task policies. Here are some examples of LIRF on 3 different tasks. The first one is a simulated door locking task where the robot must rotate the latch into the locking position after closing the door, but the latch is behind the door and occluded so that locked and unlocked doors look the same. As we see here, LIRF still manages to learn the correct behaviors. In the second task, the robot must build a stable tower with blocks of different weights, but it must leave the blocks to know their weights so that it can place the heaviest block as a bottom. Here we see that LIRF learns to undo non-stable stacks once it identifies the heaviest block, which is visualized in green here. Finally, we also evaluate the LIRF on a real robot screwing task in which the robot cannot observe whether the screw is tight or not without trying to twist it open. Once again, our method LIRF learns correct screwing behaviors. Of course, we also evaluate our method quantitatively against several baselines. As all these tasks are designed to be partially observable, the baseline image-based exemplary reward method VICE performs poorly. On the other hand, our method LIRF is able to solve all of them with significantly higher success rates. Furthermore, if we allow LIRF to keep trying until the evaluation policy is happy, we can get a better performance. We even compared LIRF to methods that have access to actual privileged information, like demonstrations, manually engineered verification behaviors, and ground truth state rewards. And we find that it performs on par or better than all of them. So it looks like the rewards provided by our interactive reward function policies did indeed produce good task policies. But what does the LIRF policy do? It tries to open the door by pulling the door handle, pokes the bottom block to examine if the block stack is stable, and gently unscrews the valve to verify if it is tightened. Through these behaviors, the LIRF policies are able to distinguish between success and failures. So we are excited about the performance of our algorithm LIRF and plan to continue improving it. But one important current shortcoming is that the actionable examples can be cumbersome to provide. For example, we need to show the LIRF policy around 100 physical examples of locked doors in the door locking task in order for the LIRF policy to learn the actual verification behavior. One solution could be to train safe LIRF policies that avoid destroying positive actionable examples. In conclusion, we have presented LIRF, a framework for training example-based interactive reward function policies that evaluate task policies. And the LIRF can provide rewards to train task policies and verify task policy execution in the loop in several partially observed tasks. Thank you all for listening. Happy to take any questions.